So now let's move on to question 4 and question 5. So again, we have this Darlington pair, and we are supposed to find R prime E Q1 and R prime E Q2. Obviously, you didn't know that you're supposed to calculate R prime E Q2 when you were calculating R prime E Q1, but I'm going to solve them together. Okay, something to note about Darlington pair is to just be careful about the currents here. So as you saw in the previous example that I solved for questions 3, when the input current or the base current enters Q1, it gets multiplied by the beta of Q1. It gets multiplied by 150 times, and it appears at the emitter, IE1 we call it. Now this current is exactly going to go to the base of Q2. So it is equal to IB2. Then IB2 or IE1 get multiplied by the beta of this transistor Q2. So it gets multiplied by 150 times more. And then it appears here at the emitter of transistor number 2. So keep that in mind. So something you can always say about R prime E of Q1 and Q2 in Darlington pair is that if you calculate R prime E for Q1, let me just make sure that this is focused, then this is 25 millivolt IE1, right? The DC voltage, the DC current at the emitter IE1. And IE1, we just mentioned that it's basically going to be IB2. So it's the same as saying like this is IB2. Now we know that IB2 is the emitter current of the transistor Q2 over beta DC2 plus 1, or you can just ignore plus 1 here. So you can write IB2 as it is like this, IE2 over beta DC2 plus 1. So now if you just divide this by here and just bring this to the top, then becomes beta DC2 plus 1, or again, you can just simply say beta DC2, 25 millivolt over IE2. Now 25 millivolt over IE2 is exactly R prime E Q2, because if you wanted to calculate R prime E Q2, it would be exactly 25 millivolt over the DC current of its emitter. So you see, in Darlington pair, you can always say R prime E Q1 is always beta DC to the transistor, the second transistor, plus 1 R prime E Q2. Or you can simply say beta DC 2 R prime E Q2. Now, if we calculate R prime E Q2, then we can have R prime E Q1. So let's do that. Let's calculate R prime E Q2, which is 25 millivolt over IE2. Now, how do we calculate IE2? Like always, I like to go backward because then I know what I'm looking for. Now we are looking for IE2, right? Ohm's law says that IE2 is the voltage here, VE2. Let me take it out here, VE2 over RE. So I'm going to write that down. IE2 is VE2 over 1.5 kilo ohm. here, an NPN transistor, we have it, VE2 is 1.7 volt minus the voltage here. I call this voltage VE1 because it's at the emitter of the first transistor. So I write it VE1, or you can say this is exactly VB2 because they are at the same point. Sorry, VE1 and VB2, they're at the same point. Minus 0.7 volt over 1.5 kilo. Now, so we have to find VE1. Again, VE1 is minus 0.7 volt here of this VB1, the base current here. So it becomes VB1 minus 0.7 volt. This is VE1 minus 0.7 volt over 1.5 kilo. So you can say that it is VB1 minus 1.4 volt over 1.5 kilo. Now we have to find VB1. I hope you remember how we calculate VB1. VB1 is right here. Right here, you can calculate VB1 by calculating the voltage division that happens between these two resistors. So it's going to be, let me just write it here, draw it here again. So we have a 33 kilo ohm, 22 kilo ohm. We have VB1 here. This goes to the ground. This is connected to the VCC, which is 10 volt. As always, it's easier to just ignore this connection because IB is very small. So 10 volt. That means that VB1 is 22K over 22K plus 33K multiplied by 10 volt. This becomes 4 volt. So VB1 is 4 volt. We continue it here, we put it here. This becomes 2.6 volt over 1.5 kilo. It becomes 1.7 milliamp, right? Yes, 1.7 milliamp. Now we found, what did we find? This is all IE2. IE2, IE2. Good, we found IE2. So let me just come down here. R prime EQ2 becomes 25 millivolt over IE2. So 25 millivolt over 1.7 milliamp. This is going to be 25 over 1.7. It's going to be 14.7 almost ohms. So you see, this is a small resistor. Now we found out that R prime EQ2, Q1 is beta DC2 times R prime EQ2. Sorry, I'm just going to silence this. Now, if we calculate REQ1, beta DC2, 100 times this 14.7 ohm, we get almost 1.47 kilo ohm for REQ1. So that's how you should solve these two problems. Obviously, I did a lot of explanation, but watch this again. If you didn't understand it, pause it and see if you can follow. If you have questions, you can always email me.